Okay, hi class, hi those that are rewatching this. I'm going to go ahead and get my screen ready to share with y'all the notebook that I prepared for today. So there we go. I think this is correct. Yes, excellent. And I'll go ahead and make that big. Oh, I did the wrong one. What? Forgive me. I got confused all of a sudden. I think I went to the clicked the wrong window. All right. Is everybody seeing the notebook okay? I believe you are. Okay. I think I saw Guy nod his head. Excellent. Thank you. Now I'm getting my other window fixed here. Well, I'm on Linux and it's not always letting me do everything that Windows did with this. So anyway, I'll just get started. Guy, just chime in if something's not clear. Okay. I want to go through feature engineering, and I had planned to use this session to show how to use Lasso to also reduce features. But it turned out that this was not a good way to show that. So I will show it in the next class as part of what we're going to do in the next class too. So let's just get these imports ready in the notebook. And we're going to create some fake features. And all I want to do is go over an example we've done before. We're going in profit mode. We're saying for a very basic feature engineering problem, this is how our Y values are produced. Again, this is not real life. This is profit mode. We're going to know ahead of time the model that created the labels. So when we look at the labels, and here we're in a perfect world where we have no noise, we have this very smooth arrangement of data points. So this is just to show a very, very basic feature engineering exercise. Well, we're modeling without feature engineering first and using that model to make predictions and evaluating model performance. So we have already imported linear regression from the scikit-learn library, and we're going to start out with saying the intercept is false and that the copy of X, we don't need to do a copy of X. Now we fit the model with those very basic labels we created and our X values. We are going to then look at our one coefficient that we get and round it by 3. And then we're going to say that this is Y predicted no feature engineering. So we put in the values of X again, and we'll go ahead and do an R² score. So we run that, and I meant to, we'll look at the output down here. So we'll do a scatter plot of our, excuse me. Yeah, this is the scatter plot of just our labels and our features. Then we're going to plot our features against that prediction with no feature engineering. And we're going to go ahead and look at our R² score and our coefficient value. Well, we know ahead of time that we should have gotten, if it were using X², we would have had a coefficient of 2. But the R² score is not that, it's not horrible, but it's not that great. This would be better than using nothing. So it's okay, but can we do better? Of course we can. So we ask, will feature engineering give us a linear relationship? Because let's look at this. The assumption to use linear regression is that we have linear relationships. And this is not a linear relationship between X and Y. So if we do look at, if we do a scatter plot of x squared, again, this is a NumPy array, so we can just square it directly and it'll square all the values in it. And we look at that the Y for very basic feature engineering that we did in profit mode. Now, yes, we have a linear relationship, but remember it's x squared versus our labels versus our Y. So we repeat the modeling steps now with the engineered feature. So we're going to do a fit with x squared and our labels and the same things as before. And now that those have been generated, we'll visualize them. And wow, this is great. We have a perfect model because we have no noise. And we've got our coefficient back. And we didn't have a y-intercept, so this model is absolutely perfect. But that's a very basic feature engineering problem. And let's stop and just remind everyone, what does it mean to do feature engineering? We have our features, which are our inputs. We have our labels, which are our outputs. And we're looking for models that will predict well. But sometimes the values that the features that we start with, they're not in the form that we really need them to do to have a model that predicts well. So sometimes we have to engineer features, meaning put those features into other functions that will result in linear relations and give us basically better predictions, so that we have to actually engineer a new feature or a new set of features. So to get a little more advanced, let's start now with two features, x1 and x2. And we'll go back into profit mode. We're going to have 2 times x1 squared plus 3 times x1 times x2 plus 2.5 times x2 squared. And we'll go without noise for simplicity of explanation first, but we'll do one with noise too. So we'll run that. Now we have our labels, but we're just calling this Y basic feature engineering, not very basic, just basic. Now we're going to get pandas and Plotly loaded for visualization purposes. And I'm going to create a data frame from using NumPy, using the horizontal stack feature. I'm going to stack x1, x2, and that Y basic feature engineering label set, but I'm going to reshape that to a column array so that they're all columns. And here are my column names. And I'm just going to look at the top 7 lines of this. Now it looks like I'm not going to see the top 7 lines. Oh, I didn't print them. That's the problem. This would have to be the last line in the cell for it to print. But what is Plotly showing us here? That's interesting. Okay. And I didn't necessarily need to do that, but it's a good check. So now let's place all the features as received into one NumPy array. So in other words, we're having all the features as one group. So I do that horizontal stack trick again, and I do a quick inspection, and these aren't sorted by magnitudes. So let's try to model without feature engineering first. Oh boy, that R squared score is horrible. So how can we possibly do better? Well, let's see if we can do better by using polynomial features. Now, polynomial features are awesome, but they're only throwing out powers of your features and interactive powers too. Well, what do I mean? Well, let's import polynomial features. And let's say we've got an order of 2. We're only going to go second order. And I would start this way even if I didn't know the problem was that way in Prophet mode. I would keep experimenting with increasing orders of magnitude for the polynomial features. But what does it actually give us? Let's look at that. Well, it gives us the constant value of 1, meaning x to the all of these to the 0. But it gives us x1, x2, our original features. But because I said second order, it starts at x1 squared, then says x1 times x2, and finishes with x2 squared. If I had had to the 3, let's just look at that real quick for fun, see what it tells us. I've got 1, x1, x2, x1 squared, x1, x2, x2 squared. Now it goes up to the next order. x1 cubed, x1 squared times x2, x1 times x2 squared, and x2 cubed. So all of these are powers come up to third order. All of these come up to second order. Both of these come up to first order, and this is to the 0th order. Remember, any number raised to the 0th power is 1. But let's go back to 2. I just wanted y'all to see that. And you might be asking, well, is it ever practical to go up to 4th or 5th order? Yes. I had a real life problem where I had to do that. Guy, yes.
It's in fact, it's 2 questions. I think it's reminders. Maybe you can tell me later. We will find these answers. Okay. So the first one is why ever I will need feature engineering. Yes. Okay. In our case, the linear regression, it cannot detect nonlinear relationship between the input and output, but we can use other modeling methods and it can find the relationship. So why we need feature engineering? This is the first question. The second question, is feature engineering affecting the original, which is clearly its affect the original distribution of the inputs? That means how the inputs, it will be different after feature engineering, and how we can enter, let's say, how we can explain the findings according to that. So this is the 2 questions that come to my mind. By the way, I'm as I told you, I'm reminding you, I'm not, especially for the second question. We have original features. Now, forget if we are using fake data right now, but we have original features and we perform kind of engineering to it. Now, this engineering, we are dealing with different values at that as input. How this map to the original values? This is the question.
So now I believe your question will be answered both now and as we go through. But the first question's a good one, I think. Remember, we're pretending we don't know how we got the labels. We don't know the model for the labels. Now, we do know, but we have to pretend we don't because we're trying to get the value of using fake data, which a big part of that's prophecy mode. So we don't even know that feature engineering is going to help us yet. We are experimenting to find out if it will help us, but we're doing it in Prophet mode. So when I was doing real life problems, like I said, I had to go up to 5 orders of magnitude and experiment with other portions of this to get the results I was looking for. But now, could you repeat your second question though?
Let's keep it for later because
okay.
I have a note. I have a note for this one, for this
Excellent.
question.
But because we did, oh yeah, go ahead.
Yes, the main target, I think the main valuable target for us, it's reducing the size of the model itself by performing better data, by using better data. So
Exactly.
when we are with this small step, we can find, if possible, the best engineered feature to go for the linear regression. It's better than going for deep neural network to solve a small issue, for example.
Yeah.
So this is the main benefit for it. I'm just reminding, sorry for that. The second
No.
question is related how to map the engineered features to the original features to know how to explain the findings.
Yes.
So this is maybe we can make it later or maybe another session because it
No.
can go very deep.
Yeah, no, those are great questions. Now let's remember we've included the y-intercept, or yeah, the bias they call it, and we may or may not need that. So that's for bias or a y-intercept. We don't want that this time, but we could experiment with it and without it and see if which one is better. But we already know the tools by which to find that out, and that would be the p-value. And I'm just realizing now I could have used Lasso to determine that too, but it's probably better we do that separate. So if we wanted to remove the bias from polynomial feature class, well, you could just do it this way: include bias equals false. Now, I want to take you for a moment to this page. This is can y'all see the scikit-learn document? Excellent, thank you. Okay, so this is great because we just go here and we know what we need to send in. The degree level, do we only use the interaction terms? We'll look at that both ways so you know what that is. Do we look at the bias? Do we look at the order? I'm not going to go over order now, but you can study it here. These are actually written quite well, but sometimes to understand them better, you really need to experiment, like taking an option, going without that option. But you can see they're doing the same problem we were just doing. And then they have examples, and then they show the methods that belong to the polynomial features class. So we can fit with the X, you give it the features, and it figures out the polynomial terms it's going to need to add. You can do it straight away, like do a fit and transform. So you already going ahead and get back the polynomial features, the engineered features, that is. Or you can do a separate fit and then a transform. But remember, this is important because you might be doing a fit on a training set, which we're not doing today, and then doing a transform on your test set. You can't do the fit on your test set. You have to only do it on your training set and then apply it to your training and test set with the transform. And then we're going to use some of these too, where we say we get the feature names, we get the parameters, but you can also set the parameters directly. And I'll show you what I mean by that. That's the parameter names, basically. Okay, we'll go back to our notebook now. So again, now I'm going to show you, okay, what happens if we take out that bias equals, or say, include bias equals false. And I'm doing this to just look at the first 4 rows or 3 rows and then all the columns. But now, nice. Hey, up here we have the ones. You can see right there for that. But at this point now, we just have the x1, x2, x1 squared, etc. Everything without the bias term. Now, let's just take a quick look at interactive terms only to see what that gives us. Well, it's interesting. It still gives us x1 and x2. Why? Because they're interactions at the first order, but at the second order, it only gives us x1 and x2. Well, that's interesting. Meaning I only want interactive terms. I don't want the single terms, the single feature terms. And so if we raise this to 3, let's just do that. It'll go fast. Oh, no, because there is a reason that didn't work on 3. I'm trying to think what it would have been. We'll come to that another time. That did not do what I intended, though. Okay. So now we had that bad value up above. Let's see, and we already know it's going to work good, but let's run this model. Oh, wow. This is amazing. It got the exact correct weights. Why? Because we don't have any noise. It got a perfect R² score. But look, we still have X1 and X2 in there. So those are 0. And you're like, well, wow. It even knew that we didn't need X1, X2, but wait, where there's no noise. What will happen with a little bit of noise? And we need to realize that we might have to try many levels of orders, like I said, to get good model metrics. Okay, so let's add some noise. How do we do that? We set a fraction. We get the max. We're using a NumPy function to get the max value from an array. And we're going to multiply that max value times noise fraction. And that will give us Y noise. And then we can go from negative Y noise to positive Y noise, create 100 points like we've been doing, but add that to our label. Okay, so great. Now we've got noisy labels. What can we see? Oh, crap. We've got close to 2. We've got close to 3.5, and we've got a little further from 2.0. But now we have actual values. And if I run this over and over, this could get worse and worse. It just luck of the draw, because it's creating random features and random noise. Now this R²'s not bad, but we might, in the good course of doing good machine learning, we might ask now, well, let's look at a correlation matrix with our values. So I've defined these for the columns. I've put my features into a data frame. Oh, look. Now these ones, of course, they're okay, because that's directly x2 squared to x2 squared, et cetera, for all these. But when we see these out here, oh, shoot. X1 is correlating to X1 squared. Of course it would be. And X2 squared is correlating to X2. So how would we do that? It's collinearity. And you can look back at previous lessons to see how to determine which features to remove in greater detail. But we'll just do a simple example here. This little trick right here is just saying, go from the second column to the end and use all rows. And we're going to, basically, that's going to remove X1 and X2. And then we're going to do a model fit again with TempX. And we're going to look at the coefficients. All this is just fancy stuff to help us visualize what we're doing. And so with X1 and X2 removed, we get 0.98351. Let's just look up. What was it with all of it? This is a little higher, 98354. Again, don't fall in that trap. Once you know you've got collinearity, you're only comparing between the ones where you're eliminating features from the collinear groups. So that's when we remove X1 and X2. What if we removed X1 squared and X2 squared? Much better. No, it didn't. Excuse me. What happened? Oh, yeah, this is much worse. So we would conclude that we should remove X1 and X2 because we got the better accuracy for that case. So the model is better with X1 and X2 removed, as we knew it would be. Okay, now how do you take this further? We need to remember, I just want to remind you of this. When we're not using fake data, we're using real world data. We don't know the best case. That's why we have to do all these checks. I'm gonna reduce features initially, just which feature set is best. Then I'm gonna throw polynomial features at it to see if I can get more accuracy. But again, we don't know, should I include a y-intercept in this? We might already know that, but we might want to test it again at this point. Should I use interactive terms only? Should I use the original features and the engineered features, or just the engineered features? These are all things we have to test, but we now have adequate tool set to do that. So we're literally just throwing polynomial features at this in the hope of finding greater accuracy. So you have to explore and experiment a lot. Now, a family game that I'm suggesting. Create fake data features and labels, but do not share the model you use to create the labels. And if you don't have anyone to partner with, I can do this for you. I'll give you some fake features and fake labels, but I won't tell you the model I use to create the labels. Then you share, but if you have a partner, you can share your data with a friend and they can share theirs with you, and you challenge each other to find the correct model whose weights you alone know. And that would be really cool. Now, this gets to Guy's question, I'm pretty sure. A challenge question. Will polynomial features always work for feature engineering? I don't think so. But if you look deep enough into the math, oftentimes polynomial features will work, even if polynomial features aren't the best. So you could look endlessly for the best engineering of features, and that it would be more than just polynomial features. Let's say it's cyclical. Well, you might need a trigonometric function like sine or cosine. That can be a form of feature engineering. But you would have a clue of that, hopefully, by just doing a scatter plot of your features versus your labels. And then you could see the patterns in there. We could also, and I showed you the challenges with this, but we can do plots of each feature against the label or the labels. And if things are in the right zone, you can detect, well, will a polynomial help with this? Or if you see something like that, oh, I can't use polynomial features, but I can apply my own feature engineering in the form of sine or cosine. And then what are other ways that you can find engineered features? Well, way one, and I'm going to edit this as we go, is plots. And this doesn't always work, but it sometimes does. Plots of feature, each feature versus label. And I'll do this because it might be multiple labels. Now, does anyone want to take a guess at a second way to deal with this? How can you get engineered features other than polynomial features, or what you could figure out from doing number one? Number one over here, because I've done the cheat numbering over here, but I'm talking about over here. Well, I'll tell you one. You do deep learning, because what's the power of deep learning? It can figure out the feature engineering on its own. But what's the downfall of doing that? It's this. Yeah, it'll do the feature engineering on its own, but it won't tell you what it did because it's buried in a neural network. And so what is the shame in that? I've lost the insight of what features were engineered. Now, how can I detect what features were engineered? I can use explainable AI, post explainable AI. If you've heard my explainable AI talk, it's a spirit of, oh, I would have to do a control model wrapped around the neural network to discover, oh, if I hold everything constant but only change one feature, how does the output change? And you could see that relation and you could figure out what feature engineering it did. But that is very time consuming and painstaking, especially if you have a very large feature set. So this is what, I mean, yes, deep learning is awesome if you only need predictions. But if you need the deeper understanding too, to pass back to your organization, understanding the engineering of features that work best is a great feedback to the rest of the organization if they're caring about growing in their data science skills. So I will just say deep learning, but at a loss. Maybe recover the loss, with SHAP or line. Now, does anyone have a last idea? And this would be pretty advanced, I think, but maybe not. Just in my mind, I'm thinking of something that would be pretty advanced. Well, you see how we're just kind of indiscriminately, like as the orders of magnitude increase for polynomial features, we're throwing more and more engineered features into the mix, and then we're having to go back to remove the features that aren't valuable, and we can use p-values with that. We can use lasso that we haven't shown you yet, or you can use did it create collinearities? Let's maintain the best feature from each collinearity group. So you can do all of that, and that's a lot of work. But since we're throwing a lot of engineered features into our feature set with polynomial features, we can create our own group of engineered features. A lot of trigonometric functions, a lot of other algebraic functions and calculus functions. We just throw slews of stuff at it and keep experimenting and refining. But it's a long game. So throw many engineered features that are not polynomial based into the mix of engineered features to experiment with. Probably could have worded that better. I ended with a preposition, but still, throw many engineered features that are not polynomial based into the mix of engineered features. I'll just say for experimentation. To find ever better engineered features. And just be aware, let's say you're doing a real problem like this and your manager's understanding why you're pushing ahead to keep doing feature engineering. Hey, it's a trade-off. Now, in that spirit of that trade-off, you're trying to get more accuracy. But if you get a decent accuracy out of the gates, put that model into production and keep trying to improve it outside of production. Then when you can convince your stakeholders, I want to replace our current model with this one. I've continued to work to get it more accurate. Oh, great. Let's put that one in production. I'd like a little more time to experiment even further. Yeah, go further. At a certain point, the priorities may change. And it may be, I know you want to get it better still, but the amount of energy it's taking to get a little more improvement's not worth it. And we have this other problem. It's like a George Lucas movie making situation. Good machine learning models are never completed. They're just abandoned, right? At a certain point, it could be that no matter how much more work you do, the data is too noisy to get much better improvement. So you might get this point where, yeah, I'm doing a lot of work to get a little improvement, but it's really, I'm being held back by the quality of the data now, not by the quality of the feature engineering. And in fact, you can have your search for engineered features obscured by noisy data. And it could be that the noise isn't bad. It's just, you can't go any deeper because of the amount of the data noise. So if you've done your best to get the least amount of noise possible and to clean your data and to condition it well with scaling, everything we've learned, you've reduced the original features down to the best set. You've engineered, you've even tried principal component analysis. You've done all these things, but at a certain point, you got to abandon the model. And let's remember what the wise Dr. Box taught us. All models are wrong, but some are useful. And if we look, it would have been great to do a plot, but basically we know when we see this R squared score right here, well, that's not 1.0, but because we have noise, we're never going to get to 1.0. And in profit fake data mode, we know that because we did get with zero noise, we got a perfect model. The only reason, sorry, not that one. Sorry, little pause. It's not that one we're concerned about. It was this one. This was our best model. We knew it would be, but look, I'm not exactly at 2.0. I'm not exactly at 3. I'm not exactly at 2.5. Why? Because of noise. Can I approach those? Yes, by having even more data. I'm only using 100 points. Once I get to 150 points, I should rerun this and get new model weights. But
would you please check the chat, because Greg, yes, he has interesting question. Yes. And there's also interesting comment from Minha.
Now I might need you to help me with the chat because I'm wondering where my chat window went.
Okay, I'm going to read the question from Greg.
Perfect.
Can we risk overfitting by over increasing the degree of orders in polynomial feature engineering?
And I did find the chat, but thank you for that. So Greg, yes, but remember, one of the outcomes of overfitting is collinearity. So that's why we check the correlation matrix to see if we have collinearity. By the way, in a future class, we're going to have more methods to detect collinearity, but always correlation is going to be a good tool for you there. Now, the other thing, we have been religiously trying to avoid this overfitting by reducing down to the best feature set. How do we do that? we've seen at least with p-values, we're going to cover using lasso also. And you can use ridge too, but there's a reason I'm going to encourage y'all to always start with lasso and not think about ridge so much. So yes, we always risk it, but we do these tools to keep reducing it down to the best feature set so that we're not overfitting. And then, yeah, and Greg, you'll get there as you keep thinking through this and improving your coding skills. This thing you mentioned in your second comment will become a thing of the past. Okay, there are quite big literature on non-parametric regression, which suggests a different set of basic functions. I'm trying to reword this. Polynomials are one of them. Splines, kernels, wavelet. Okay, so splines are more, that's more of a smoothing technique in my mind. I could be wrong. Kernels, again, that's a way to help you reduce your data set. If I'm understanding you correctly, I would have to go review wavelets. I don't remember that well. I just haven't seen it in so long.
What I meant is more about there are actually a theory about how to select best basis function, which can actually represent entire data, and polynomial is just one of them. So it's not just one way. There are many different ways to do it.
Yeah, and in fact, that's great, Minha. Thank you for chiming in. Very good point. Let's remember.
Think about the Fourier transform, right? You can actually approximate any function with the set of Fourier transforms, right? So that's kind of similar idea. You can actually have different basis function to represent any kind of possible functions.
This is what he's saying is so good. And the reason that it can be complicated, though, to do what Minha is saying is when we have multiple features, to tease that out, to look at each one with respect to label. Because when I do a plot of one feature against the label, when there's multiple features, well, that label's actually been being influenced by the other features too. I'm just hoping to see some clue of the relation, but Minha is absolutely right. For the many cases where we have one input and one output, but there could be a lot of engineering that we could use. There are some great tools to help us discover what engineering we need to do. But in my mind, and I could be wrong, I think that's limited to simpler cases. One of the reasons what we do is hard is because when we have like gobs of features and we're just trying to do a good prediction, remember these polynomial features, we're just like blitzing our feature set with these engineered features and trying to reduce down to the set that gives us what we most need. I hope that's making sense.
Yes, I think what you are talking about is essentially interaction between the variables in terms of the causal model terminology. This is the so-called causal terminology. The more variable you have, there are so many different combinations you can make. So it has been, a big problem for a while. I think there are some attempts already to have some non-parametric representation with the multivariate space. But again, practically, that sounds good in theory, but whenever you're trying to implement, you face causal dimensionality. Simply,
yes.
The space is so large.
Yeah, no, great point. And I'm sitting here thinking of more I want to say, Minha, but I think it's better for our PCA lecture. By the way, guys, there are current limits to what we do. And this thing with engineered features, it's not completely trial and error, but it is a little bit of trial and a lot of processing trial. So the methods we learn to reduce features, like with p-values, and we will see it with lasso too, the methods we use to figure out what features aren't important, or the methods we use to find out which feature of a set of features that are collinear, which of those features we're going to keep from that collinear set is just repetitive work. Okay, find the engineered features that are of no value, find the best engineered feature to keep among a collinear set, and then we get a value and we might try the next order of magnitude and do the same thing over again, but just add the new engineered features at that time. We can discriminately do that. And then, yeah, Minha just put a link in there, so y'all capture that before it goes away. I hope this was helpful. Let's take a break before mentoring. Guy, anything to add or question before we go?
No. Thank you.
Yeah.
I think I like it.
Oh, thank you.
And sorry for the interruption at the beginning, but I found it's good to understand why sometimes we follow the feature engineering.
Oh,
As you said, it's good to go to deep learning, but also it might be very costly. So that's why we have to think twice before going there.
I actually appreciated the timing and nature of your questions, but one thing I failed to say, if we're going to deep learning, which can be helpful in a predictive sense and very complicated in an explanation sense, we have to have a lot more data.
Yeah.
Deep learning is a hog for data. In other words, to get it accurate, it needs a lot of data. So we may not be able to go to deep learning right away. We may have to do the best we can do with the best feature engineering we find. So, but if you could still get benefit by feeding a set of engineered features that have been reduced as best as possible, and then try a neural network that can do some additional feature engineering, at least we had most of the explanation. But the neural network does have the chance to give us a better prediction because of the nature of its abilities.
Yep.
So, all right, great. I will see y'all in mentoring. And then again, in our pipeline class chat, if you got questions, add them there. Minha, love having you here. Everything you add, please